In this hour, we will talk about the Bode plots, which are very useful visual tools for frequency response analysis. Okay, here is what they are. Okay, Bode plots or Bode diagrams, okay, are separate graphs of the gain and phase versus log frequency scale. Okay, the gain and phase of some transfer function versus log frequency scale. Okay, now let's try to understand what that definition tells us. So let's pick an arbitrary transfer function. Okay, suppose that it has the following form: Ks, s plus alpha 1, and then s plus alpha 2 times s plus alpha 3. Okay, a second order transfer function. Now we're interested in the gain and phase. Okay, the gain, the magnitude of h omega, and the phase of h omega versus omega. Okay, so we want to obtain those relations visually. So first, therefore, let's write h of j omega, which is k j omega plus alpha 1, j omega plus alpha 2, j omega plus alpha 3. Okay, now it turns out that it's better for our purposes to write this, or to rewrite this, in the following form: k alpha 1, alpha 2, alpha 3 times j omega, and then all these terms, namely 1 plus j omega over something. Okay, so that 1 plus part is important. So we have 1 plus j omega over alpha 1. Here we have 1 plus j omega over alpha 2, and we have 1 plus j omega over alpha 3. Okay, so that's our h omega. Now let's have a look at both the gain and the phase of h omega. So that produces the following: h j omega magnitude, okay, the gain, equals the magnitude of k, because k could either be positive or negative. Okay, it's a real number, but it could be positive or negative. Whereas alphas, namely minus of which are either zeros or poles, they're all positive. Okay, so that means we're dealing with poles and zeros that are all on the open left half plane. Okay, so that produces k alpha 1, alpha 2 times alpha 3, and then we have the magnitude of j omega, which is omega, and then the magnitude of the other terms: 1 plus j omega over alpha 1, 1 plus j omega over alpha 2, and 1 plus j omega over alpha 3. So that's our gain function. As for the phase, h j omega, that equals, okay, the phase of this term here, since alphas are all positive, so that is determined by the phase of k. If k is a positive real number, then the phase is 0. If it's negative, then the phase is 180 degrees. Okay, so the phase of k, okay, plus the phase of this term, plus the phase of that term, and then from that we subtract the phases of the first order terms in the denominator. Now the phase of this term is independent of omega, and since it's purely imaginary, it's 90 degrees at all frequencies. Okay. And then we have phase of this, which is arctangent omega over alpha 1. Arctangent omega over alpha 1. And then we have the, from that we subtract the phases of the terms in the denominator, namely arctangent omega over alpha 2 minus arctangent omega over alpha 3. Okay. Now this could either be positive or negative, as we said. Excuse me, K could either be positive or negative. Therefore, this phase is either 180 degrees for negative K or 0 degrees for positive K. Okay, so let's put that down. This is 0 degrees or 180 degrees. 0 for K positive and 180 degrees for the other possibility. And as for the 90 degrees, it's coming from J omega term, and J omega term is due to this S term here, namely due to the 0 at the origin. Okay, this is due to the 0 at the origin. Okay. Now, one thing that's nice about the phase compared to the gain is that we have a bunch of terms. What we can do is we can draw all those terms separately and we can add them up. So when we're working visually, subtraction or addition is much simpler than multiplication or division. Okay. So to make use of the same simplicity, the gain will now be expressed in a different way. Okay. So let's put that down. Note that it is easy to sketch the phase H J omega, and the easiness is due to the fact that it can be written as summation of a bunch of simple terms. Okay, so plot each term separately and add them up. Okay, once again, adding or subtracting is easier when you're doing sketches, when you're doing plots, than multiplication or division. Now, to make use of the same simplicity, the gain H omega magnitude H G omega magnitude is expressed in the following new units, which we are to introduce now, in decibels. Okay, in short, it's written dB, B written capital. Now, this is definition of the gain expressed in dBs, decibels. H J omega, okay, the gain expressed in dBs means the following. What you do is you compute the log of that positive real number, okay, the magnitude of H omega, and then you multiply that by 20. And the new number that you obtain is the gain expressed in decibels. Okay, so now let's write the gain once again, but this time in terms of our new units. Okay, so h j omega magnitude expressed in decibels, okay, equals, since we're taking the logarithm of this fraction, all the products, they become additions and divisions become subtractions and so on. So everything is much easier from the sketching point of view. Okay, so we have 20 log of k alpha 1 over alpha 2 alpha 3. Okay, so that's that. And then we have plus 20 log of magnitude of omega, but omega, well, omega is always positive, therefore we have 20 log omega, plus 20 log 1 plus j omega over alpha 1, okay, and then from that we subtract the 20 logs of these first order terms because they appear in the denominator, okay, so minus 20 log 1 plus j omega over alpha 2, and finally minus 20 log 1 plus j omega over alpha 3. Okay, and now that's the gain in terms of dB. Now let's now analyze each type of term separately. Okay, we begin by the constant term. Okay, namely this term, k alpha 1 over alpha 2 alpha 3. K alpha 1 over alpha 2 alpha 3. Okay, let's call them all together as k0. Now 20 log magnitude of k0, namely k0, or the magnitude of k0 in decibels, is positive if, since we're logging it, if this is greater than 1, and it's negative if it's smaller than 1, okay, between 0 and 1, that is. If k0 is larger than unity and it's negative if k0 is smaller than unity. Okay, but in either case, this is independent of frequency. Okay, so therefore the gain contribution of the constant term is well, constant because it's constant term. So independent of omega. Likewise, the gain, the phase of this k0, which equals the phase of k, because only k could either be positive or negative. The alphas are all positive, we take. The gain of the phase of k0 is 0, okay, if k0 is positive. Otherwise, it's 180 degrees, okay, if it's negative. So k0 equals 0 degrees if, and 180 degrees if k0 is negative. But in either way, it's again constant, namely it's independent of the frequency. Okay, so there's really not much interesting stuff going on with the constant term, so it will be easy to deal with that. Let's now move on to, well, before moving on to the other type, although it's obvious what the result will be, let's obtain the sketches for that constant term. have the following two plots. That's gain, and let me put here the phase, omega. This is K0 expressed in dB, and this is the phase of K0 versus omega. Now, suppose this is 0 dB. Okay, and here we have the constant term. Okay, that's a horizontal line for all that's fixed. So the gain is, or the function, this function is constant for all frequencies. Okay, it's the same for all frequencies, and this value is 20 log of absolute value of K0. Okay, because we're expressing that term in terms of dB. Okay, so let's mark the frequencies, omega 1, let's say omega 2, and omega 3. This is 10. Let's say this is 100. And the frequency is marked, although for the constant term it will not make difference in the shape, okay, because it's a fixed horizontal line, but for other terms it will be important. So how we mark the frequencies on the frequency axis is through using log frequency scale. Okay, so this is called log frequency scale. Okay, and then as for K0, it's either 180 degrees if K0 is negative. Okay, this is for K0 negative, or it's constant at 0 degrees for K0 positive. Okay, now what we mean by the log frequency scale is the following. In log frequency scale, the axial distance, okay, that is the distance that we see with our eyes when the frequencies are marked, between two frequencies, omega 1 and omega 2, let's say, is proportional to log omega 2 over omega 1, which is log omega 2 minus log omega 1. Okay, so here note that this distance and that distance, as seen by the eye, are the same, and that's because from omega 1 to omega 2 you move 10 times, okay, and then you take the logarithm of 10 over 1, which is log 10, which produces 1, okay, and then from 10 to 100 again you move a tenfold, omega 3 over omega 2, again 100 over 10, that produces log 10, that produces 1. So here we have the distance here, therefore, in log frequency scale, and the distance here, they are the same, because the ratio of omega 2 to omega 1 and ratio of omega 3 to omega 2 are the same. Okay, now let's move on to the other type of term, namely to R0 at the origin. Okay, second term, j omega term. Okay, so we had a j omega term in our example due to the 0 at the origin. We may have had also a pole at the origin, then we would be dealing with 1 over j omega term. But since we're, for instance, for the gain, we are dealing with the gain in terms of decibels. Therefore, the treatment for j omega and 1 over j omega, they're almost identical. Okay, it's just a matter of plus or minus. So this term is due to a single pole or 0 at the origin. Okay, and it contributes 20 log omega, okay, to the gain. If it's a 0 at the origin, its contribution minus 20 log omega if it's a pole. Okay, to the gain and plus minus 90 degrees to the phase. Again, it's plus 90 degrees if it's a 0 at the origin, and it's minus 90 degrees if it's a pole. Okay, plus for 0 and minus for a pole at the origin. So let's quickly obtain the gain and phase plots for this j omega term. Here is the gain. Omega, and we're measuring things in dB, and let's mark the frequencies as follows. Okay, so let this be 1 radians per second. This is, okay, we go 10 folds to the left so that it becomes 1 over 10 radians per second. And suppose that this is 1 over 100 radians per second. And then these are equal distances, okay, in log frequency scale. Therefore, from here to here we go 10. From here to here we should also go 10 folds. So that means this is 10 radians per second. And here we have 100 radians per second. Okay, so that's how we mark the frequencies, and the distance here is called a decade. Okay, a decade. Okay, we will give the precise definition soon of a decade. Okay, now let's also mark the vertical axis. Suppose this is 20 dB, and let this be 40 dB. And this is minus 20 dB, and suppose that this is minus 40 dB, and so on. Okay. So let's start with a 0. Okay, so we're talking about plus 20 log omega. At omega equals 1, log 1 is 0, so 20 times 0 is 0. So our curve must be passing from this point here. At omega equals 10, log 10 is 1, 20 times 1, 20. So we're passing from this point. Okay, also. And then at omega equals 100, log 100 is 2, and then 20 times 2, 40, and so on. And similarly for the frequencies less than unity. So for 20 log omega, this is the line, okay, which doesn't much look like a line because I wasn't able to draw it properly. But this is a line in this in these scales, dB versus log frequency, and that's R 20 log omega. Okay, and now if this appears in the denominator, if it's due to a pole, then what we have is 20 log and then magnitude of 1 over j omega, and that's minus 20 log omega. Okay, so what you do is, if you have minus 20 log omega, you take this, you take the reflection of this line with respect to the horizontal axis. So that produces this. Okay, so this is minus 20 log omega. Now these are straight lines, and how we measure the slope, note that whenever the frequency goes tenfold, we rise 20 dBs. Okay, from 1 to 10 we rise 20 dBs, from 10 to 100 we rise a further 20 dBs, and we reach 40 dB, and so on. That's why the slope of this line is called 20 dB per every tenfold, and every tenfold is expressed using this word, okay, a decade. So the slope of this curve is 20 dB per decade. Likewise, the slope of minus 20 log omega is minus 20 dB per decade. Okay, so here the slope is 20 dB per decade. Likewise, slope of this is minus 20 dB per decade. Okay, so let's be precise about what we mean by a decade, and this is the definition. In log scale, the distance between two frequencies omega 1 and omega 2, let's say, is measured in decades. Okay, and this is what we mean. The distance between omega 1 and omega 2 equals omega 1 over omega 2 decades. Okay, you take the ratio, and then you take the log of ratio, and then the magnitude of that number is the distance between those two frequencies, and in decades. Okay, for instance, from 100 to 10, the ratio is 100 over 10. 10 log 10 is 1, so the distance is 1 decade. Okay, or let me squeeze an example here. Omega, this is 10, this is 100, and here, somewhere here, we have 20 radians per second. Okay, this is from 10 to 100. There's a decade. Okay, this is 1 decade. From 10 to 20. Okay, 20 over 10, it's 2. Log 2 is approximately 0.3 x. Right, 20 over 10 is 2, and log 2 is approximately 0.3. Therefore, the distance between these two frequencies is 0.3 decade. Okay, or from distance, the distance between 20 radians per second and 100 radians per second is 100 over 20 is 5, and then log 5 is approximately 0.7. So this distance here is 0.7 decades, and so on. Okay, and how about the phase? The phase of the j omega term, well, we can squeeze it here because it's very simple. It's because it's pure, for all frequencies, it's purely imaginary. Therefore, the phase is either plus 90 degrees or minus 90 degrees, but in either case, it's always constant. Okay, therefore, the phase is simply this, okay, either 90 degrees or minus 90 degrees. This is the phase for j omega term, and this one is the phase for 1 over j omega term, okay, the term, if j omega term appears in the denominator. And let's also talk about the third type of term that appeared in our example transfer function, namely the first order term. Okay, third type, first order term. One plus j omega over alpha. Okay. If it appears in the numerator, this is the term. If it appears in the denominator, then we have 1 over that thing. Okay, so it's either plus or minus 1, the power. Okay, now the gain of that term, okay, the magnitude of 1 plus j omega over alpha, and we're dealing with it in terms of decibels. Okay, at low frequencies, by which we mean, okay, so let me put it here. Okay, now this term gain at low frequencies, and by low frequencies we mean omega less than alpha. Okay, so, alpha is the term that appears in the denominator here. In decibels, we have 20 log 1 plus j omega over alpha magnitude. Okay, now it turns out, especially if you're expressing things in decibels, it turns out that when omega is less than alpha, this can be approximated with simply 1. Okay, so we can ignore the imaginary part if omega is smaller than alpha, and what we have is 20 log 1. Log 1 is 0, therefore 20 times 0, 0. So what we have is 20 log 1, that equals 0. Okay, so for low frequencies, and by low for the gain we mean omega less than alpha, taking it constant at 0 dBs seems to be a good approximation. At high frequencies, by which we mean omega frequencies larger than alpha, 20 log 1 plus j omega over alpha can be approximated by the magnitude of its imaginary part only. Okay, so here we can ignore this 1 here, and what we have is 20 log omega over alpha, and that's 20 log omega minus 20 log alpha. 20 log omega over alpha, and that's 20 log omega minus 20 log alpha. Okay, and that's a line with 20 dB per decade slope. So let's combine those two approximations. Okay, this is omega. This is 1 plus j omega over alpha plotted in decibels. This is our 0 dB line, and then we have 20 dB. Let's mark the frequencies as, suppose this is alpha over 100, this is alpha over 10, this is alpha, this is 10 alpha, and so on. Okay. Now, the low frequency approximation is, and by low frequencies we mean omega less than alpha, is very simple. It's just a 0 dB constant line. Okay, so for all frequencies up to alpha, our first order term can be approximated by this so-called low frequency asymptote. And when the frequency is larger than alpha, omega greater than alpha, then what we have is, what our approximation is 20 log omega minus 20 log alpha. Okay, so let's also figure out that curve. When omega equals alpha, what we have is 20 log alpha minus 20 log alpha, that produces 0. So our high frequency asymptote passes through that point. Okay, omega equals alpha and the gain equals 0 dB. And then at, let's say at 10 alpha, what we have is 20 log 10 alpha over alpha, which is 20 log 10, that's 20. Okay, so at 10 alpha, we're passing from this point. At, let's say 100 alpha, 100 alpha over alpha is 100, 20 log 100 is 40. Okay, so at 100 alpha, we're at 40 dB and so on. So that means we're rising with constant slope, and slope is obviously 20 dB per decade. So this thing is the so-called high frequency asymptote. And this part here, the constant part, is low frequency asymptote. Okay, and the slope of high frequency asymptote is 20 dB. 20 dB per decade. 20 dB per decade slope. Okay. Now let's also talk about the actual curve. So these two lines, or half lines, were just approximations. And the question, of course, is how good is that approximation? Okay. So, first of all, before talking about the validity of the approximation, note that 20 log 1 over 1 plus j omega over alpha. Okay, so if we were dealing with a term that appeared in the denominator, then the gain would be 20 log of the magnitude 1 over that thing. Okay, but the nice thing about working with the log is that this is simply whatever this is, then you multiply that by minus 1. Okay, so that equals minus 20 log 1 plus j omega over alpha. So as far as our sketch is concerned, so that means if you want to obtain the plot for this term, 20 log 1 over 1 plus j omega alpha, all you have to do is take this term and take the reflection of this term with respect to the horizontal axis, okay? Or just multiply everything by minus 1. So that's that. And as for the validity of the approximation, it turns out that the farthest the actual curve is from the approximation, from the asymptotes, is at the frequency where two asymptotes meet, namely at omega equals alpha. And our approximation tells us that at alpha, the gain equals 0 dB. Now let's figure out the actual gain, okay? for that frequency, and that's the farthest that the actual curve is from the asymptotes. So let's compute 20 log 1 plus j omega over alpha at omega equals alpha. Okay, alpha is where the two asymptotes meet. Now this equals, plug in omega equals alpha, alpha over alpha 1, so we're talking about 20 log of magnitude of 1 plus j. Okay, the magnitude of 1 plus j is square root of 2. So that's 20 log square root of 2. Square root of 2 is 2 raised to the power 1/2. Therefore, that's 10 times log 2. And log 2 is approximately 0.3. 10 times 0.3 is 3. Okay, so just mark here 3 dB, and that's the point where the actual curve would be at omega equals alpha. And at all the other frequencies, the distance between the actual curve and the asymptotes will be less than 3 dBs. Okay, so the actual curve would look more or less like this. And so on. So this is the actual curve. Okay. Okay, now let's also say a few things about the phase. Phase of the first order term. 1 plus j omega over alpha. And that's arc tangent omega over alpha. Okay. Now, again, we will talk about the asymptotes at low frequencies. Okay, now we have to be a little bit careful. What we mean by low frequencies for gain and low frequencies for phase, it turns out that they are different, okay? As far as the phase is concerned, for low frequencies we have to go lower than this, okay? Omega less than alpha, okay? And a good approximation, or an acceptable approximation, seems to be omega less than alpha over 10. Okay, so at low frequencies, namely omega less than alpha over 10, this thing can be, as far as the phase is concerned, can be represented by its imaginary, by its real part. If omega is much smaller than alpha over 10, we can ignore that, and then we're talking about the phase of 1, a positive real number, which is 0. And at high frequencies, omega larger than 10 alpha, okay? So that's what we mean by high frequencies for phase. For gain, high frequency meant omega larger than alpha. Okay, for omega greater than 10 alpha, 1 plus j omega over alpha, this time we can ignore the real part, and what we have is, we have a purely imaginary term, the phase of which is 90 degrees, okay? So for high frequencies, we can approximate this as 90 degrees. Now, we considered the ranges, omega less than alpha over 10, and ranges omega greater than 10 alpha. Now there's a range we still didn't touch, that is for omega between alpha over 10 and 10 alpha. And for those frequencies, alpha over 10, 10 alpha, 1 plus j omega over alpha can be approximated by a straight line. Okay, in log frequency scale, of course. So let's put these on a plot and obtain the phase diagram.
Omega 1 plus j omega over alpha. This is 0 degrees, 45 degrees, and say 90 degrees. Here we have alpha over 10 alpha and 10 alpha. Okay. Now let's obtain the asymptotes for low frequencies, omega less than alpha over 10. The phase can be approximated by 0 degrees. Okay, so we have this as the low frequency asymptote. And for high frequencies, omega greater than 10 alpha, the phase can be approximated by a constant 90 degrees, and that makes our high frequency asymptote. Okay, this is low frequency asymptote, this is high frequency asymptote, and for the intermediate frequencies, the straight line happens to be a good approximation, and by straight line we mean the line that connects these 2 points, okay, namely the end points or the beginning points of our two asymptotes, low frequency asymptote and high frequency asymptote. And then we connect those 2 points, and that's our intermediate frequency asymptote or approximation. This is also an asymptote. Now this asymptote is a straight line. Let's figure out the slope of its line from alpha over 10 to 10 alpha. So that makes 2 decades, and in 2 decades it raises from 0 degrees to 90 degrees. Therefore the slope is 45 degrees per decade. Okay, that's 45 degrees. So the slope is 45 degrees per decade. And as for the actual curve, it happens to be something like that. Okay, this is our actual curve. So asymptotic approximation, therefore, is quite a successful one. Okay, and that's more or less what there is to tell about the phase of the first order term. One last thing to mention is that had we had a term, first order term, that appeared in the denominator, namely if we had to deal with the phase of 1 over that thing, clearly all we have to do is take this and multiply by -1, or take this and reflect it with respect to the horizontal axis. So what happens is then we have the 0 degree low frequency asymptote, minus 90 degree the high frequency asymptote, and we have the straight line with slope minus 45 degrees per decade that connects the two asymptotes. Okay, so note that the phase of 1 over 1 plus j omega over alpha simply is minus what we have studied. Okay.